Like many of you, I love cellulose. And you know what they say, if you love someone, you shouldn't try to change them. So in my work, I'm actually looking for ways to not change cellulose while still advancing its capabilities. This is in direct contrast to common ways we see cellulose in technology. Remember those rapid COVID tests we all took? They rely on a chemically modified form of cellulose called cellulose acetate. Cellulose acetate is used because it links to antibodies, the biomolecules that detect infection. But it isn't compostable. And in fact, the EU now categorizes cellulose acetate as a single-use plastic. This is a shame because native cellulose is compostable, and that's probably my favorite thing about it. I wanted to learn why native cellulose isn't used in biosensing devices, like the millions of single-use COVID tests and pregnancy tests that go to landfill each year. I learned that there's no easy way to link biomolecules like antibodies, enzymes, or DNA probes to native cellulose. So technologies that need biomolecules to stay in one place will turn to modified cellulose or plastics as a solid support. The goal of my work is to link biomolecules to native cellulose, and I was able to do this using biology, not chemistry. I designed a protein that has never existed before that is two hands, one that grabs onto cellulose and one that can grab onto any biomolecule. The cellulose grabbing hand is inspired by natural proteins found in soil bacteria. These proteins evolved to hold tightly onto cellulose to aid the bacteria in decomposing plant matter. The other hand grabs biotin. Biotin is a common tool used in molecular biology that can be attached to any biomolecule using a kit that you can purchase from any major science supplier. I had to figure out how these two hands could come together in a way where they're still functional. So I used computational modeling to evaluate many different designs, and then genetically engineered bacteria to produce the most promising two. I am now performing experiments to understand which protein offers stronger bonds to both cellulose and biotin-tagged biomolecules. Besides allowing for compostable biosensors, I believe my protein can also radically reduce plastic waste from biomanufacturing. The production of many pharmaceuticals and foods relies on immobilized enzymes. The surfaces those enzymes are linked to are discarded to landfill at their end of life and persist there. This happens on the order of hundreds of thousands of tons annually. I believe my linking system can change this footprint since it's entirely compostable and can replace these materials. I was able to preserve what I love most about cellulose while expanding its applications. I hope this work inspires you to also use our gifts from forest without compromising their best qualities. Thank you.